K3 and
integral-affine structures.
Integral-affine structures on the sphere.
Thank you very much. So I would like to thank the organizers. Thank you very much for the invitation. I'm happy to be here. I like Moscow. I really like Moscow. Doesn't matter when. So Moscow is great. So I've been working on this problem for a long time. So it's possible that maybe some of you heard maybe some earlier very incomplete versions. Heard me speaking about this, but so now the work is finally done. So we had a conjecture, now we proved it. So I'm going to explain. Now finally I understand what's going on. So the general topic is this. So the general topic is compact moduli of algebraic varieties. And so, as we all know, a very rough split between the types of varieties that we have is with ample canonical class, so general type, with zero canonical class, so Calabi-Yau, and with negative canonical class, so Fano. And for varieties of general type, there is a compact moduli which is quite similar to mg bar, to the Deligne-Mumford compactification for curves. And so this is the moduli of stable pairs. The pairs are of this form. B is a divisor on a projective variety X, and the pair has SLC singularities, and then Kx plus B is ample. So for such pairs, there is a moduli space. So maybe some people call it KSBA. So maybe I'll just put it here so I don't have to explain too much about it. So in the talk of Harold Bloom, that appeared already, and Odaka proved that under this condition, so when the log canonical class is ample, this is the same as K stable. So that's by Odaka. All right. So there is a moduli space of K stable varieties and pairs. Now for the negative canonical class, there are several talks here already. So one looks at K-stable Fano varieties, semi-stable, polystable, etc. And so that seems to be the right moduli space to consider. And then there is the middle case. And so this is the case I want to consider today. So this is when the canonical class is 0. And then there are two approaches. So you can go that way or you can go that way. And they're different. They lead to different results. So I believe Odaka will speak about these moduli from the K-stability point of view. So I'm not going to preview his talk. You will hear that yourself. So I want to talk about the moduli in this sense. So these will be more ordinary moduli of varieties, of ordinary varieties. This is a moduli of some generalized objects. So I will stick to ordinary varieties. And so what are the varieties with trivial canonical class? There are abelian varieties, of course. And so those are easy. And then there are K3 surfaces, harder. And then you can look at Calabi-Yau threefolds, say, and maybe hyperkähler varieties. So even harder. So on this scale, again, I will in this talk I will stick to this case. Now, from this point of view, from the point of view of moduli and degenerations, abelian varieties are an easy case. So I think everything has been understood. So there is a complete picture. So let me briefly say what I mean by this. So what is the picture? So the picture is this. So there is this moduli space, AG, and again, just for the purposes of, so I can call it SLC, or I can call it this KSBA, so I don't have to explain. So there is this moduli compactification of this space. It's a moduli of such pairs, but the pairs are with kx plus b ample. And in this case, kx is 0, so you need a b. You need an ample divisor. And for principally polarized abelian varieties, there is the theta divisor. So that's the b, just the theta divisor. And so when you look at such pairs, in this case, because b is ample, you can take your divisor with a very small coefficient, epsilon b, and then sort of you can ignore what kind of singularities b has. It will all be about x, really, and how b contains or does not contain some strata of x. So you get this moduli space, and its normalization is toroidal compactification. So it's a toroidal compactification. There are infinitely many toroidal compactifications for AG. There are sort of like toric varieties. They correspond to fans. But there is one special fan. And so this fan is it's called the second Voronoi fan. Okay? So there is this statement. And then so you have a compact moduli. So in particular, for any one parameter family, there is a limit in this moduli space. So one parameter families then have a description here, a clear, very easy description, and here's what it is. So for any one parameter family is described by a tropical abelian variety. So tropical principally polarized abelian variety with a tropical theta divisor. So theta divisor. So there is this combinatorial object which captures the combinatorial essence of the situation. It was known 100 years before. I mean, these objects under different names were known 100 years ago. But anyhow, so now people call them tropical varieties. And this second Voronoi fan, so this Voronoi fan, second Voronoi fan, it is really the moduli of these pairs. A tropical abelian variety with a tropical divisor. So the goal is what I want to do. The goal is to have the same for K3 surfaces. So what I want is I want this moduli compactification. I want to understand that compactification, or maybe the normalization of it. And I'm really hoping that maybe it's toroidal. And then I want to know what the fan is. And it would be great if yeah, this is also what I want. I want some tropical K3 surface with a tropical divisor. And I want the fan to be really the modular space of these tropical objects. So now I'm going to explain this picture a little bit better, so a little bit more. So you will see what is it I'm trying to generalize. So let's say we have a one parameter degenerating family of abelian varieties. So abelian variety here of dimension G, I will write as C star to the G modulo Z to the G. And so I will have a family of such varieties, and T will go to 0. There will be some one parameter family. So what's changing is it's changing the way the Z to the G is embedded into C star to the G. There are different embeddings. There is a one parameter family. Now, this embedding I can write as a G by G matrix. And the columns of this matrix will be those vectors. And as T goes to 0, so the entries here will be, I can write them as Uij T to the Bij, something like this. And Uij will be invertible. And the T, well, T is that parameter that goes to 0. So it's invertible when T is not 0, but then it degenerates. So any one parameter family of principally polarized abelian varieties can be just simply written like this by formulas. And this is the period matrix. And this period matrix has the continuous part, and it has the discrete part. And this discrete part also, that's what that is responsible for the combinatorics of the situation. So this Bij, then that's a matrix. It's G by G. It's symmetric, and it is the integral valued. If the degeneration is maximal, then B has to be positive definite. So if it degenerates maximally, then in the limit, this period matrix is just 0. So it's kind of the maximal degeneration. Okay, so that's the data. So that comes from the polarization. So in the case of principal polarization, so polarization is an additional data. If you write it just like this, it's just a torus. So the data of a polarization is a data of a line bundle. And so by Mumford, for example, this data is an identification of two matrices, which makes this matrix symmetric. So
does the transform mathematics respond for depending on dual varieties?
So maybe I can explain this way. So one way to write this abelian variety is Z to the G modulo Z to the 2G, right? And so you get the torus, and you can pick some vectors to be the basis, and then there is lambda. And so there are Riemann relations for this to be not just a torus, but a projective abelian variety. And the Riemann relations say exactly this, that this matrix is symmetric, and that the imaginary part is positive definite of lambda. And so the relations between these two is that I exponentiated this part. So these are exp of 2 pi I, this omega ij. So that's what they are. So this matrix was symmetric, so this matrix is symmetric. So when you write it in this form, then some logarithms appear. But if you, after exponentiating, this really becomes just algebraic like this. So this is called, this could be done by classical methods, but Tate and Mumford realized that when you write it in this form, that it looks pretty algebraic, so you can in fact do it not just over C, but over any complete discrete valuation ring, over any normal complete ring, so in mixed characteristic, etc. So that's called the Mumford construction, or Tate-Mumford construction. Okay, so what I want to explain is this, this combinatorial object. So here's what it is. So we have this B, and B is just a bilinear symmetric form like this. And for, let me from now on just talk about this case, just abelian surfaces. So I'm going to generalize this to K3 surfaces, so let me talk about surfaces. So very simply, this is a 2x2 positive definite symmetric matrix. And now there is some fan here. So what is the support of this fan? Where does this fan live? So it lives in the space of such matrices. So B, which are symmetric and positive definite and integral valued. So that's a three-dimensional space. So if I take so this lives in R3. And this cone, let me call this cone C. So there is a cone and the fan. So fan, the support of this fan is the closure, the rational closure of this cone. This means that on the boundary, I'm only adding rational points. There is the interior, and then the rational rays. Now, the fan here is the reflection fan, otherwise called the Coxeter fan. So, and in this case, it's also the second Voronoi fan, and or Dynkin fan, or Coxeter fan. So this Coxeter fan just corresponds to this A2 tilde diagram, Dynkin diagram, and here's what it is. So it's very easy to describe. So you start with a cone where this ray is x squared. Let's say this ray is x squared, this ray is y squared, and this ray is x plus y squared. And so that's your three rays, and so that's your elementary cone. And then you start reflecting. And so if you reflect here, then there will be again a triangle, and this will be x minus y squared, etc. So it's a very kind of famous picture. So you get this triangulation of the hyperbolic plane. It is SL2Z invariant. So SL2Z acts on this. So there is this very from many points of view, very familiar picture. So now I will take a matrix, a particular matrix somewhere here. So this matrix is then, so it will be A x squared plus B y squared plus C x plus y squared. And A, B, C, if I take it in the interior, well, so they're non-negative, but if I'm in the interior, then they're positive. And so they're integers. So that's my starting data. And so for this point, there is a one-parameter degeneration. There is a type of one-parameter degeneration. Say again? X squared, y squared, x plus y squared. I know. Okay, I lied a little bit. So, okay, someone noticed. Okay, sorry. I tried to simplify. Okay. So there are these three integers, and then I'm going to tell you what is the tropical abelian variety and what is the tropical theta divisor and how it describes this degeneration. And okay, so here's how it works. There is also a shift, like there is a linear part here to make it integral valued. Let me skip those details. So here's what it is. So we have lambda, and on lambda we have this bilinear form, and I consider B as a map from lambda to lambda star, and because lambda, I took lambda to be integral, then the image is a sublattice here. So I have lambda star, and inside I have a sublattice lambda. And so the tropical abelian variety is this lambda star tensor R modulo lambda. So it's a torus. It's isomorphic to R squared modulo Z squared. But it's a torus with integral points. Because I have, these are the integral points. I'm dividing by a subgroup. And so this comes with finitely many integral points. And so on this lambda, there is a Voronoi decomposition. So invented by Voronoi, a paper published in 1908. So this used in applied math a lot. So the way it's defined is I looked at the points which are closer to this point, closer to any other integral point. So in this case, there is a hexagon. And then the points which are closer to this point, closer than to any other, there is this. And so this is called the Voronoi Polytop, and then there are copies of it. And it all covers the plane. So there is this picture. Now I map it in here. So in here there is this B of this Voronoi decomposition. So this is called the Voronoi decomposition, those polytops. And so there's B of Voronoi B, and I divide it by lambda. And this is the tropical theta divisor. And so the way it looks is you start with this picture, and then you map it by B. And let me tell you what happens. So what happens is that, so this hexagon here, it's fractional, because these are the integral points. But when you apply the map B to it, then the image is integral. And you get a hexagon again, but this hexagon has integral lengths. They go in three basic directions, and their lattice lengths are A, B, and C. A, B, and C. And then there is a tessellation by such hexagons. So let me summarize. You have a torus with well-defined integral points on that torus. And inside you have this polyhedral structure, which is called this divisor, this codimension 1 subset, which is called the tropical divisor. And that describes the one-parameter degeneration. How? So here's how. So for every vertex, at every vertex here, there is a fan. You consider it to be a fan. And this fan is a fan of a toric variety. That toric variety is an irreducible. So this, first of all, describes you the central fiber of the degeneration. This central fiber has several components. irreducible components. They're in bijection with the integral points here, with the vertices. So for every point you have a fan. So this is a fan of P2. And so here, modular translation, there are two of them. So the central fiber is a union of two P2s, which are glued along 3 lines. So that, first of all, that gives you the central fiber, just this picture, this tropical divisor. Secondly, it actually gives you the whole family, the whole one-parameter family. This is how. So you take a cone over this. So this is an infinite picture. Take a cone over it. And consider that to be a fan. It's an infinite fan. You get some infinite toric variety. Once you divide it by z squared, then this is the family of abelian varieties, of degenerating abelian surfaces. That's the answer. So it's all easy because it's all toric. So this tropical divisor, in fact, gives you both the central fiber and the entire one-parameter family. No. So it's so the dual picture. There is a dual picture here. So the dual picture is these triangles. So there are 2 kinds. So these are the P2s. This is the polytop picture, toric picture. So this is a P2. This is a P2, and they are glued along. This is side 1. This is side 2, and this is side 3. So these are. And it's a degeneration of abelian varieties. So it has the cohomologies are the same as for abelian varieties, not as for K3s. So H1 of O, for example, is 2-dimensional. So as for abelian surface, the regularity is 2. Okay, so. That's it. So that's the picture we would be happy to have for K3 surfaces. And let me quickly say the challenge. Oh yeah. Let me finish. So I also said this, that this fan, in fact, is just the moduli of these polyhedral pictures. This is a polyhedral object, kind of, and it has some moduli, and this moduli gives you the fan. All right, so thinking of this, what are the degenerations of this? How can this tropical divisor degenerate? It can degenerate, A can go to 0, or B can go to 0, or C can go to 0. And so then this hexagon will become a foregone. And so that's when one of these ABC is 0. So then you're on the edge of this triangle, of this cone. If both of them are 0, then you're on the ray. So the cones are precisely the cones where this picture stays, the combinatorial type is the same. So this B you can move around. That will just change the lengths. Algebraic degeneration will only correspond to the cases where A, B, C are integral. But if you vary them continuously as real parameters, then there will be some symplectic varieties instead of algebraic here. And but anyhow, so this cone is exactly where the interior of this cone is where this type of the hexagon stays the same. Then it degenerates. And then as you pass the wall, then it flips, and you get a hexagon in some other direction, like I guess in this direction. And then you cross another wall, and you get a hexagon in the third direction, etc. So this fan is just the moduli of this tropical abelian varieties.
What is the name of this object?
Huh?
You said that this object is 100 years old.
It's Voronoi. It's Voronoi fan, second Voronoi fan. Right. So Voronoi was a Russian-French mathematician, and his goal was just to classify positive definite quadratic forms. Just say, positive quadratic forms are of types 1, 2, 3, 4, 5. In dimension 2, there is just one type. So, that was his goal. So this is, we want up to GLGZ, classify all quadratic forms into some cones like that. So he was not an algebraic geometry. So, okay. So now that's what all of this I want to generalize. And so finally I can tell you, I can say it in at least, well, in one case. Well, really, how many cases do I have? Maybe 12 families I can do now. We can do this way. But the biggest one of them is this. So let's F2 be the moduli space of polarized K3s. So this is a K3. This is an ample line bundle, a polarization, and of degree 2. And so this is the biggest family. It's 19-dimensional. And maybe later on I'll say, we have like 11 or 12 families that we can do this way. And I mean, the hope is do it in general, right? Okay, so here's the statement. So you take F2, this SLC, this moduli space. So it exists. Now, again, we need a divisor. So what's a divisor? So to apply this machinery, one needs some ample divisor. And you cannot just take an arbitrary divisor in L, because then the dimension of the moduli space will change. Instead of 19-dimensional, you would have to add the dimension of this linear system. Exactly. But these are double covers. The non-unigonal ones cover P2. The unigonal ones cover F40, Hertzsprung surface F4 with the section contracted. They're all double covers. So this L, in the non-unigonal case, L gives a double cover. And so the divisor is that B is the ramification divisor. So there is a canonical choice. So that's the divisor I'm going to take. And then this machinery gives a compactification. And so the statement is that there is a toroidal compactification, which I will describe. It will correspond to a Coxeter diagram like this. And there is a map. This map has some positive dimensional fibers somewhere, but its Stein factorization looks like this. And so there is a semi-toric compactification. So there is this theory of toroidal compactification, and then Luoyanga generalized it. There is Luoyanga's theory of semi-toric compactification. And they also correspond to fans, or maybe I should say semi-fans. So those are like fans, but some cones are infinitely generated with infinitely many rays. So that's a theorem. That's a theorem. So Alexeev, Engel, Thompson. This diagram. And then another theorem is this description of one parameter families. And yes, this is the normalization. So this is finite, this is the normalization. This is the Stein factorization for that. And one parameter families correspond to, I want to say tropical, but I will say integral-affine. spheres plus this. I said tropical before, but this time I will say integral-affine divisor. So integral-affine is a generalization of toric geometry. So this what are the hard problems that one is faced with here? Degenerations of K3s is not toroidal, is not toric. For abelian varieties, the period map is extremely simple. It's just, C starts with a G modulo Z to the G. The period is this matrix. It's just linear algebra. Periods of K3s are extremely hard, impossible transcendental theory. So the period map is not known. The inverse period map is not known. There is the abstract Torelli proved by Shafarevich and Pitetsky-Shapiro, but it's a very tricky proof. Uses the density of Kummer surfaces and the moduli space. It's extremely indirect. So nothing here is as easy as abelian varieties.
So what is the round K divisor?
Of the double cover, of the 2-1 cover. So let me repeat. So any surface of of degree 2 comes with a canonical involution. There is a double cover. There is the ramification divisor.
So the second theorem states for the maximal degeneration. What about the draw complex being
Right, and so we have a picture for that too, and maybe I'll explain that. I'll be happy to explain that too. So maybe I should say first here what happens for abelian varieties when both say A and B go to 0. So as you can see, this 2-dimensional picture becomes 1-dimensional picture. So this 2-dimensional torus degenerates to a 1-dimensional torus, just R mod Z. And so this is the same that happens here. This sphere, where is it sphere? It degenerates to an interval. So a finite interval. So that we also describe. Okay, so let me see, where am I? So let me say a few words about this. So this sphere with 24 singular points. So the sphere with 24 singular points appeared in many people's work. The first time the sphere appeared, to my knowledge, is in the work of Kulikov. So Kulikov says that if you have a one-parameter degeneration of K3 surfaces, then it has a Kulikov model, and a maximal degeneration corresponds to a triangulation of a sphere. The dual complex of the central fiber is a triangulation of a sphere. So those Kulikov models are highly non-unique. They're elementary. There are flops. They differ by flops, but it's highly non-unique. It's because the canonical class is 0. So to have uniqueness, you have to add this divisor. That makes the limit unique. But anyhow, so Kulikov, Persson, Pinkham, so they already had this sphere. This 24, to my knowledge, first appeared in a work of Friedman and Miranda, where they noticed that this picture is sort of 24 steps away from being toroidal. And maybe I'll explain. So it's not toric because there are these 24 singular points. I'll explain. So and then let's see. Then Pelham Wilson and Mark Gross, they had some paper about Hausdorff limit, metric limit of K3 surfaces, and under some conditions, their limit, they proved that this Hausdorff Gromov-Hausdorff limit is a sphere. it's a metric sphere with 24 singularities. And then, most explicitly, there's a paper from 2006 or so by Kontsevich and Soibelman, where they say explicitly. So instead of the torus, you have to take a sphere with 24 singular points, an integral-affine structure on it. And then, well, that's a great idea, but then the question is, well, how does it all work? What are these 24 points? How do they move? Do they collide? If they collide, what happens? How does it all work? And so I'm going to explain how it all works in this case. So I will start with generalizing this Coxeter diagram. So for abelian surfaces, it's just this triangle. It's HU tilde, affine HU. And for these K3 surfaces, it's a little more complicated. And so here's what it is. So there are 24 nodes in this graph, in this Coxeter graph. These are the first 18. Then there are 3 more. Then there are 3 more. And this is the Coxeter graph for the lattice here. So these vectors, all of them are -2 vectors. They are roots. They span. The span is this lattice. It has rank 19. So that's the lattice. And inside of this N, this lattice is, let me tell you explicitly what this lattice is. So it's H is the higher, this is H, plus there are 2 copies of E2, and there is a copy of A1. So it's a lattice of signature 118. It's hyperbolic lattice. And these are the roots of this hyperbolic lattice. So this lattice, there's a reflection group acting on it. The wild group, it's the reflection in those -2 vectors. And this is the diagram for the fundamental domain in this for this reflection group. So it's a hyperbolic lattice. There is a cone C. This is the cone of vectors of positive square. And the fans, toroidal compactifications of F2 correspond to fans whose support is the support of the fan has to be the rational closure of this cone. That means you take the interior, and then on the boundary you only add the rational rays. So, and that's it. So that's the kind of cone. Now, here let me declare the fan. So the fan is just the Coxeter fan for this reflection group. So there is a fundamental domain. This fundamental domain is its vectors v such that v dot ri is greater than 0. That's a single fundamental domain. And then you start reflecting. So you start reflecting, and these reflections cover this whole rational closure. Yeah, so some of these vertices are at infinity. So some of them are rational rays at infinity, and so the statement is that this is the fundamental chamber for this reflection group. Its images cover this. Now, This is a fan because all fans are finitely generated with rational generators. So it's a fan. It is invariant under the reflection group, certainly, by definition. It's also invariant under the isometry group of this lattice. So the isometry group is 6 times bigger than the reflection group. And this difference is, so there's isometry group, there's this reflection group. The quotient is S3. S3 is the symmetries of this graph. Uh-huh. No, it's the Picard lattice of the mirror dual, K3. So there is the Dolgachov-Nikulin mirror symmetry. Take the generic surface in that mirror family. So these K3s, the family is 19-dimensional, the Picard is 1-dimensional. For the mirrors, Picard is 19-dimensional, and the family is 1-dimensional. So there is a mirror family. These are the -2 vectors, and this is the Picard lattice of the dual K3, described by Kondo in 85 or so. So it's a well-known K3 surface, but it's the dual K3 surface, mirror dual.
So in this case, the automorphism is finite?
Yes, that's exactly, because this reflection group has finite index. In the isometry group, this mirror dual K3 has finite automorphism group. Mm-hmm.
It has only finitely many -2 curves. No.
I mean, the criterion from Torelli, the criterion is the automorphism group is finite if and only if the Weil group has finite index, right? And that is true. So, yes, I think these are the only 24 -2 curves on that surface. There are only 24, and they're all on the board. And this is how they intersect. These intersect by 2. These intersect by 6. That dotted line is 6. So, all right. So what I'm going to do, I'm going to take a point in this fan, and I'm going to describe a 1-parameter degenerating family of K3 surfaces with that period point. Okay. So what I'm going to do is I'm going to I will take a point in the interior of this cone. Moreover, just in the interior of this fundamental chamber, and so then I have these AIs, and they are positive integers. And so this is a period of some 1-parameter degeneration of K3 surfaces. And now I'm going to describe that 1-parameter family for you. And toric geometry, we kind of don't have toric geometry. This degeneration is not toroidal. And so I will describe all of these things for you. Sphere with 24 singular points and a family. Okay, I'll start with the sphere. Yeah, and on a sphere somehow I should have well-defined integral points. So how does that work? Okay, so here's how. So I will define these BIs, and BIs will be need room. Okay, this will wait a little bit. Now, because I have so little room, I'm going to reuse this picture. So I'm going to make, out of this picture, I'm going to make a fan. And so the fan will be, will look like this. So just take the central point, connect everything. But here there is a point in between. So that ray is short, that ray is long, that vector is short, that vector is long, that's short, long, etc. So what you have here is now a fan. This is the center of the fan. You raise the boundary. So that's a fan. That's a fan of some toric surface. Okay. So my initial I have 18 rays now. There are 18 points on the boundary, so 18 rays. So what I'm going to start with first is I'm going to draw a polytop whose normal fan is this. Okay? It will be a two-dimensional polytop, and this is the normal fan. So there will be, for this ray, there will be a side such that this ray is the perpendicular, and then so there is the 18 gon. Okay, there will be an 18 gon like this. This 18 gon will have some lengths, B3, B2, B1, B0 bar for some reason, B6 bar, and B12 bar. So that's my initial starting point. So right now it's all toric. There is this toric surface. This is the moment polytop of that surface. So I'm given some lengths BIs. That means I'm given this surface a polarization. I'm defining some ample line bundle on it. Okay? And that's the moment polytop of that line bundle. Now somehow very soon this will become a sphere. So how? So on the side B0, I will make a cut. I will say in a second. So right. So this is 0, 6, 12. So 0, 6, and 12 are the corners. So I'm going to make a cut on side 0, on side 6, and on side 12. And it's an equilateral triangle, integral equilateral triangle. This distance, so there is a distance here. It will be some number that will be for in that Coxeter diagram, there was a vertex number 18 right here in this corner. So for that vertex, there is that number A18. And I'm going to cut it like this. And then I'm going to define A0 as B0 bar minus A18. Okay? And then let's see if you can catch the pattern. It's because there are even and odd sides, because some of these are short and some of them are long. There is a little rescaling here that's necessary. Okay? But so here's what I am. So out of these numbers, out of these 24 numbers, I'm making this picture. And so the first statement is that if these are the numbers, then first of all, this 18 gon it will close. It's a non-trivial condition. You know, I have these directions, and then I have 18 numbers. Once I come back, it may not close. It's two conditions. But in that Coxeter diagram that I drew, the vectors are not independent. They are not linearly independent. There are 24 vectors that span a 19-dimensional space. And I'm just telling you that because of those linear relations, first of all, this polygon closes. And so secondly, what I'm going to do, I'm going to, so right now, all of these AIs, BIs are integral, so there are integral points everywhere. I'm on a lattice. I'm working inside of Z2. So there are integral points in this polytop. And so the next operation is to close these holes, to saw down these cuts. And so when you do this, you create a singularity. So at this point, you create a singularity. This is the singularity of integral-affine structure. So this is what integral-affine structure is. It's sort of locally, there is a Z2. But if you go around the singularity, then there is a monodromy. This monodromy is an element in SL2Z. And in this case, it's the monodromy which sends this vector. It sends this vector E1 to E1, and it sends this vector E2 to E2 plus E1. So there is an element in SL2Z which is non-trivial, and so that's why if it were trivial, then it would be just all toric or tropical. But there are these things. Now, so when you close these things, you get a sort of a polytop. This is called the Symington polytop. So Symington is a symplectic geometer from working in the state of Georgia. And so she came up with this in symplectic geometry. And so there is, what you get is the Symington polytop, and it comes with three singularities. The singularities they have these monodromy arrays, the arrays that are preserved by this monodromy, and they are parallel to the three sides. And this line, the distance from here is A18. It's for like this node in Coxeter diagram. And the distance from the opposite side is A, whatever that node was. And so it all works because of the linear relations. Okay, so now this is the half of the sphere. And what you do is you make another copy of this symmetric copy and you glue them together. And when you do that, you add 18 more singularities. 6 on each side. So 6 go that way, 6 go that way, and 6 go that way. But after this surgery, they all become parallel. So there are 18 rays that go in the same direction, that go in the vertical direction. And so then you glue to the exact copy of that, and you get a sphere with 24 singularities. 18 of them are on the equator, and then there are 3 up in the northern hemisphere, 3 in the southern hemisphere. Okay? So that's the S2 with 24 singular points. Now, what is the affine divisor?
But this is a specific property of this degree 2 surfaces, yeah?
It is the property of a K3 with a non-symplectic involution. So you can do it for any K3 with a non-symplectic involution. For example, any elliptic K3 surface has a non-symplectic involution. So elliptic, but in fact, elliptic K3s form a divisor in this moduli space. So they're automatically included. Okay, so you glue it like this, and what is the divisor? So an observation is that this sphere has an involution. And for this involution, there is a ramification divisor. And the ramification divisor is the equator. So the divisor is just the equator. So it's the boundary of this 18 gon. But because of this even-odd business, the even sides come with coefficient 2, and odd sides come with coefficient 1. So it's the multiplicities are 2, 1, 2, 1, 2, 1, 2, 1, like this. All right. Now, so that's how does that describe me a degeneration of K3 surfaces? So to get a degeneration of K3 surfaces, you have to triangulate this picture. So you have to triangulate it into triangles of volume 1. You can do it arbitrarily for as long as it's symmetric. And now what this is the Kulikov triangulation of a sphere. So what this is this triangulation of a sphere defines you a Kulikov model. And the surfaces in the central fiber are described like this. You look at any point, and at this point, if it's a non-singular point, then you have a fan. If it's a non-singular point. And a fan means that you have a toric surface here. And at a singular point, you don't quite have a fan. You have like a singular fan. And so what those correspond to, you have to take a fan here, and then you have to make one non-toric blow-up. And so this is the non-toricity. And there are 24 such singular points. So exactly in this generic case, there will be exactly 24 surfaces which are one step away from being toric. You start with a toric surface, for example, P2, and you make a blow-up on a side. And that's a non-toric blow-up. This point is not torus invariant. So in the generic case, there are exactly 24 such surfaces one step away from toric. When these points collide, and we describe exactly how they collide, all the possibilities, then for some surfaces there are 2, 3 non-toric blow-ups. But this defines you the central fiber, and finally, that's my final point. How do you, maybe 2 more points, how does this describe you a family? There is no toric geometry, what do you do? The answer is that Friedman solved this problem. So if you have a surface that looks like a Kulikov degeneration, then there is a condition called d-semistability. And if it's satisfied, then the surface is smoothable. And the smoothing has this period, has this monodromy vector. And so in this indirect way, just using, so Friedman proved kind of Torelli for such surfaces. So using Friedman's result, you have a degeneration. And and the final point is the fan. So the fan is, this is your combinatorial object. What are the degenerations? The degenerations are when some of these AIs go to 0. So either the sides collapse, or these singularities descend to the equator. And so, but that's exactly the faces of that chamber, of that fundamental chamber. So this fundamental chamber is exactly the moduli of such pictures. And then as you pass through a wall, then you mutate to another chamber, etc. I will stop here. Thank you for your attention.
These integral-affine structures come also up if you look at the image of integrable systems.
Does it have anything to do with integrable systems? Maybe, I don't know.
So the question degeneration of your K3 and integral system in the original.
Yeah, I'm sorry, I'm not unprepared for that. It's a, you know, maybe just the word is the same. Yeah. I'm not so. Okay. So I don't know this part of the story.
Special fiber would be still something like without planes.
Oh, I see. Yes. Yeah, well, okay, thank you for your question. So in fact, I did not explain to the end. So remember that picture, well, I still have it. So this picture gives you degeneration of abelian varieties. But for example, this family, so you get some threefold here. It's a family of surfaces. This threefold is singular. To have a non-singular threefold, you have to triangulate. So once you triangulate, then this cone over this picture becomes a smooth fan, non-singular fan, and that gives a non-singular threefold. And what you get is a Kulikov model for this degeneration of abelian varieties, of abelian surfaces. Now, you know, Kulikov models are highly non-unique. As I said, what makes it unique is once you add the divisor. So once you add the divisor, the following happens. These components for the vertices of this tropical divisor are the only components which are not contracted. Everything else is contracted. So there is a Kulikov model, and then there is the stable model. On the stable model, only two components, only two P2s survive. Everything else gets contracted. You know, all those irreducible components get contracted. So same here. So the only irreducible components which survive are these 18. Or if some collided, then less than 18. So so on a stable model, all of these, there is this huge triangulation right here going on. But everything inside gets contracted. So this whole hemisphere is contracted, and the southern also. And only the equator survives. And so the most general degeneration only has 18 components, and there are P2s, in fact. So it's 18 P2s. And when some points collide here, then it's less than 18.
I don't know what's going on or what, however, to me things are not like locally theoretically.
This is the, you know, as I said, this surface is one step away from being toric. This is an irreducible component. And this is just P2 blowing up at a point. But this P2 comes with the boundary. So this is the toric boundary. If you blow up a corner, if you do a corner blow up, that is still toric. But if you do a non-corner blow up, there is a lock structure with 24 singularities.
Can we do the whole thing by Voronoi Decomposition?
Yeah. So you have to start with something, and so I'm telling you, you have to start with this. Yeah? Right, and then we apply Friedman. I mean, Kawamata-Noikawa just tells you there are no abstractions. Once it's D semi-stable, it's really a reformulation of Friedman's D semi-stability in this case. Right, so you get some family of such surfaces here. It is 20-dimensional, 19-dimensional, sorry, 19-dimensional. Inside there is an 18-dimensional subfamily of D semi-stable. And that's what we deform. And it's deforms, by Friedman it deforms nicely. And now, final point. You know, what makes it really work here is this. So there is this Kondo K3 surface, this mirror K3 surface, right? But it also comes with an involution. And the quotient of that involution is a rational surface. That rational surface is the blow up of this toric surface at 3 points. It's obtained as 3 non-toric blow ups of this toric surface. So these cuts that I was making, it's just, that's what it does. So this involution just propagates everywhere here, on the mirror side, on this. And so there are two problems here to deal with. There are these 24 points that move, and then there is the tropical divisor, or this integral-affine divisor. And in this case, at least we know what the divisor is. The divisor is just the equator. And so that part of the problem is out of the way. And then we can concentrate on singularities. So that's why we were able to solve this. Oh, yeah. Type 2 is when this 18 gone, so it's a sphere. So there are 4 type 2 cusps here. And so for 3 of them, this 18 gone, for example, it collapses this way. Or it collapses that way. There are 3 ways to collapse it to an interval. And so the sphere collapses to an interval in the equatorial plane. And there is a 4th type where it collapses, this whole 18 gone collapses to a point. And this collapses to an interval sticking out. So there are, there's this very pretty picture with. Oh, type 1 is just a K3. I mean, it all collapses to a single point. That's tropical.
More questions?
Gross-Zibert, you said? Well, so I mean, the point of Gross-Zibert program is to describe somehow degenerations of, smoothings, for example, smoothings of such K3s, of such degenerate surfaces. So the way they're trying to do it is you start with a very degenerate surface, for example, just union of P2s. And for this degenerate surface, the coordinate ring is very simple. It's just toric. Okay? And then you try to deform it, modulo t squared, modulo t cubed, modulo t. And every time some new monomials appear. And so there is some very complicated procedure with adding these monomials and computing the coefficients. There are some infinite scattering trees, and there is the Gromov-Witten invariance. It's a hard job, but that's what they are trying to do. So we figured out a workaround, a different solution. Our different solution is just use this Kulikov surface and just apply Friedman's Torelli theorem to it. Then we don't have to do all that work. So that's the relation, the way I understand. Well, so we can do anything with a non-symplectic involution. There are 11 families like this, because the quotient is a Delpezza, a smooth Delpezza, and there are 11 types of smooth Delpezzas. So we can do those 11 right away. Well, then if it does not come with an involution, then the basic question is what is this tropical divisor? So here I just know it's the equator. But more generally, well, once you figure out what that is, then you can do the same. So.
You can do also for fixed point free evolution.
Oh, I see. Kind of where the quotient is maybe again a K3, Nikulin involution, something like that. We're working, but I don't know. So I don't know the answer. So.
Okay, so let's speak again.
Okay, so the next talk after the break, 4 to 7
At 2:30.
at room 4 to 7 is on the 4th floor. 4 to 7.